today we prove that kind of using synthetic division, right? I turn this r into x and look at it as a polynomial and do that. But this is more standard proof, which is reindexing technology. Remember, I don't know how you learn that, showing that the 0.33, here's an example, is a little motivation. 0.3333, if you go forever, you know, that's exactly decimal expansion of a 1/3, right? Okay, so you write it, it's 1a. This is how I first time I learned in my entire life. This first time it was taught like this. I think it's a good motivation to follow. I'm sure you've seen this one before. Because the 333 is, you know, repeated, if you shift that decimal position one time, the rest of the part looks exactly like, you know, what was that before. So if I multiply 10, what is it? 3.333, like that, right? Is that right? It goes forever. Of course, this is shifted, but if you look at this entirety with infinite number listed down, do you find the rest of the decimals exactly equal? Right? So if you subtract 10 times a minus a, that's what's happening on the right hand side. If you subtract left hand side, it's like 3.333 going forever subtracting 0.3333. So do you agree that's going to be 3? At this stage, some of the kids or some of my friends still don't believe any of this thing that this math teacher is doing. But if you believe, the rest of the part cancel out perfectly, although there's a shift, then it's just a 3, right? So 9a is equal to 3. So a must be 1/3. By looking at this decimal expansion repeated, and you can prove that. If it is a larger block, then you just multiply that many zeros, 10 to the power amount of power, then it cancellation exactly there. So in this way, kind of we can justify your answer without entering any of these geometric series. But we use this idea. You look at it here, if you look at this expression, r is there and r squared is there. If you multiply r, just like shifting that decimal, which is the same as multiplying 10, which is a common ratio in here, it does the magic. So this part, the first step is difficult to discover, but once you write that down, the rest of the part is a reindexing technique. So we consider r times, what is r is a common ratio. If you multiply r there, everything is kind of shifted. Index is shifted. If you subtract off, lots of things disappear. So if I multiply r, sk in there. Now r is multiplied at here. R itself does not have any j in it, and then you can put it inside there. 0 to k, and a times r to the j plus 1. Is that okay? Exponential law. Now you compare this one with sk. sk looks like this, j going from 0 to k, a times r in there. So if I make a substitution here, u equals j plus 1, this inside will be a times r to the u, right? Then it's going to look just like a times r to the j with the dummy variable. Therefore, it's going to, a lot of things cancel. Correct? So let's reindex it. With that substitution, so r times sk, what is it? J going from, not j, new variable, which is u. So what is the first value of u? U is a substitute like this. When j equals 0, u value is 1, right? When j hits k, u value becomes k plus 1. That's how u ranges if u is j plus 1. So now you rewrite this one, r raised to a times r to the u. That's how this thing is reindexed. And what do we do after we reindex it? We go back to j again, right? Remember, if it is u or j, it is the sum of the same thing. So starting from j going from 1 to k plus 1, you don't shift it back or anything. You just rewrite it with a different name of a variable. Does that make sense? Now you compare this one with this sk. What did we do after we make this inside exactly the same? We looked at common indices, right? Common index. So by looking at that, figure out common indices. So j, both are j. This one going from 0 to k. This one is going through 1 to k plus 1. Which are the common indices between these two sums? Starting from 1, 1 is there, all the way up to k. K is there. It goes even beyond the k plus 1, right? So these are the common index. The next thing we do after we have the common index, we write this r times sk. You separate the common index. Whatever that's outside the common index, you write it. So r times sk is it here. If you separate the common index part 0 to 1 to k, so the common index is 1 to k, so starting from 1 to k and a, r, j. Which one is do I have to add here to make it same as before? Here's 1 through k plus 1. I'm only going from 1 through k, which are common index, right? So you still have a times r to the k plus 1 left out. It didn't reach, the j did not reach k plus 1, so you must have this one outside. Let's write down sk. Sk is over here, 0 through k plus 1. 0 is not part of the common index. So you have to separate that 0. J equals 0 here, a times r to the 0, which is just a. And plus, and now common index, starting from 1, go all the way up to k. There's a common index, and there's a times rj. You write it like this. Now you notice that once you, whole purpose of this writing like this is to pull out this exactly the same term and cancel this one, right? How do you get rid of these two things? You subtract from each other. So if you subtract these two equations from each other, I have rsk minus sk, that's left-hand side subtracted, right? Right-hand side, these two things disappears, right? And a times r to the k plus 1, and here is a negative a. So sigma is gone, and if you isolate for sk, and that's our better proof than leaving that synthetic division pattern as an intuitive part. So it's r minus 1 sk, and that's a factored out, rk plus 1 minus 1. So if you isolate sk, it's rk plus 1 minus, but it's usually in literatures, they always write it in this way, backward. But as long as they're changing sign, numerator and denominator, they're at the same number. Okay? This is a geometric series. And we prove that why the geometric series of Euler version, this one looked like that. And rest of the version can be compared to this one. And so this is essential parts. End of the proof. Make sense? But if you look at the whole technique, the most difficult part to think about is just multiplying this r and pulling out this trick that this overlapping part appears. Okay, that's the proof. So let me mention that geometric series is really nice, and we just saw that how algebraically plausible it is, so we can calculate all that. But here is also interesting stuff. If I have f of x, this is not an infinite sum. It's a finite sum going from 0 to k, x to the j. Let's see. What was the formula of this one again? Not correct. Because it's not infinity. Yeah. It's not infinity, right? So it's just a polynomial. So how do you write this one? Polynomial. First term is 1. 1 minus x number of terms, which is k plus 1, divided by 1 minus x. Correct? I'm going to switch it back in here. For what I'm about to do, this is a better form. That's why I switched it back and forth. Okay. Something nice happens when you differentiate this one. And there is a series for which you have an exact formula. It's coming just full right out of geometric series. So look at this. I'm going to do the next line. F prime of x. Well, this is a finitely many terms, so differentiating each individual term is the sum of k plus 1 term. So the sum rule of a differentiation works in here. So each of them will be differentiated, right? If you have 3 terms, you differentiate each individual function differentiated. If you have infinitely many terms, you can't do that. So that's why I'm taking this procedure. It's logically correct. I can't just put an infinity there and differentiate it, because we don't have a differentiation rule that allows you to differentiate infinitely many terms at the one time. So I write down the finitely many terms so that I can differentiate it. So what is it? Each individual term, x to the j, is differentiated. J comes down, correct? And x to the j minus 1. That's how things are differentiated, right? And if you look at the right, and we just do the quotient rule goes like this: x minus 1 squared, denominator squared, differentiate the numerator is a k plus 1. X to the k, that's the derivative of a numerator, and multiply by the derivative of a denominator, minus derivative of a numerator, minus 1, times derivative of denominator, which is 1. Okay? So if you switch this x to r, we have a new series, which is not geometric, and we have a nice formula out of it. So let's simplify the numerator a little bit. This term together is going to be negative x to the k plus 1 and positive 1. This one, if you expand it, this part right here is a k plus 1, x to the k plus 1 as you multiplied it here, minus k plus 1, x to the k. Those are the two terms that fall out. So I'm going to collect it in the numerator there. So x to the k plus 1, x to the k plus 1, they're the same power. So k plus 1 and negative 1 cancel, becomes k times x to the k plus 1. And the middle term is a negative k plus 1, x to the k, and there's a positive 1 there. There's a negative and a positive 1. Divided by x minus 1 squared. Okay? So we have a new formula. J going from 0 to k, r to the j, not just r to the j, this r to the j is multiplied by j. So if you take the quotient of adjacent term, this no longer be independent of j. It's not a geometric series. So I'm going to emphasize in here, not geometric series. So we are having a new formula for non-geometric series. So this one is this whole thing with instead of x we have r, and they have a tendency of writing it like this: 1 minus r squared, and they write 1 first, and this one is a k plus 1, r to the k, plus k times, I didn't multiply really negative 1, I just reordered it because it's a square there, so signs of a numerator stays the same. So that's the formula. So this can be used in so many things, and if you differentiate one more, and we have a j squared, and all the derivative integral gives you a nice formula that is related to the geometric series. All right, I'll take a break.